With the equipment, pretty much these are exchangers here. We know where the steel is right there. So it's a very good tool. And before it wasn't, stress engineers never had much opportunity to get into it, but now anybody can have it on their computers. The reason was that piping designers are always working on it, and they figure, hey, it may not be the final, it may change. So they don't like too many people getting into at the early stage. But it's a very good tool. I think from now on everybody probably using it. And there is even a better one than this one. What we saw is a laser scan. That's, anybody seen the laser scan? Anybody heard about it?
I heard about it, but I haven't seen it.
That is amazing tool. I mean, these are nothing compared to that. That tool, you can have, they can scan the whole refinery. Everything. You can sit here and check every dimension. You can check everything so clear. You can read the labels and everything there. It's physically like you are building it. It's so clear. It's fantastic. It's not right now. We have clients has it. People who has the license, they only give you a few seats. It's not accessible to everybody. But these days with this technology, man, you don't have to leave your office. You can sit there and everything is given to you on your screen. Yeah.
So can you import from that smart plant to your Caesar, like this, the software, the last software, so you don't really need to build the layout, just use this to...
Well, I tell you what, it can be done. It has been done, but for the pipe stress purposes, it's not practical. This one discussed a lot of times. They had a lot of seminars. They had a lot of vendors came and demonstrate their software. But the reason it's not practical is the schedule differences. Is whatever they put down here is a preliminary. At that time, equipment folks, vessel group, rotating equipment, structure group, they want the load, they want the forces way before the piping is ever built, because the schedule is long time deliveries, long lead item deliveries. Here's, by the time we even get to it, they want the steel already ordered, so steel has to be designed. Sometimes this rotating equipment, they are already, the POs are out. For the vessels, same thing. So we don't get the chance, we used to, but now everybody wants everything today. The client has signed the contract today, they want it done in 2 months. For that, right away, you have to order the steel, you got to order the equipment, because they can take a year to build. So for piping guys, they don't even get a chance to put everything here. So if it's not there, there's a lot of changes. Pipe stress guys can't do their work, because number one, it's not complete. Number two, it's a preliminary, and we can't wait for the structural and the equipment people. We have to give them something. So we use whatever we can get preliminary here. We build our own in the stress program, which is Caesar program, which you guys will see, and we can get the loads and pass on to the other departments. It's been tried, believe me. This was the fantasy of all these managers for the last 25 years I have known. They can just get the model from the PDS, they just pick it up, and the stress guys can use the same here, put the information. No, it's not practical, because pipe stress, you still have to have your own information on those sketches. So it's not what we tried. Somebody suggested even link this one with our program, which is the piping stress program, with this one, and put down the structure loads right there on the steel. So structural folks can just look at there, here's the member, here's the load. And that's not even practical, because we don't have in time. Plus, for every location, if the pipe's sitting here, the guide here, we're going to have but, let's say, about 12 to 16 different numbers. You got force due to thermal in the X, Y, Z direction. Then you got deadweight. Then you got seismic. So everything has about 3 or 4 numbers, so they're hard to put on there. So this is a dream for a lot of people, for the management, for us. It's a nightmare, and it ain't happening right now. So it's off the record. I hope you didn't record it. Okay, that's good. Next again. So look at that, how nicely this helps us. This helps us to see. Now, this kind of stuff we can do right here looking at this. These are called, by the way, pipe racks. If you guys are not familiar with this, these are the pipe racks. The pipes run all the way across, and then they can branches out to the different modules and the different pieces of equipment. And this we can definitely look right here. There's a sport. We know what the distances are. We can come up with the kind of approximate loads for those steels there. And here you can see the piping, all the configurations. So we can pick up right from there. It's a very good tool. Now, there's a difference between the the other Explorer and the Smart Plant. I think different software, different clients. North Slope, ConocoPhillips, they started this one. We didn't have this before. It took almost a year for the designer to learn how to work with this one. It was a nightmare again. Every time you had to use a new software, a lot of glitches, a lot of errors, a lot of problems. It takes over a year for people to get all the bugs out of the system. But right now they're all working very well. They're nice. But I heard that they're going to even change to something else pretty soon. So these days the nicer software is available and cheaper and better. So by the time you learn this one, it's going to be something else coming up. So see how close you can get with those views here. You can support, there's a sport, there's a sport, there's a pipe sport, there's a guide here. So we can use that information right away. And, so this tells us the location of the pipes, steel, floors, ceiling, tops. So it's very handy. There you go. Okay, now this is what we talked about, the tools. What is available to a stress engineer or an analyst? Those were the items. If you have them in your folder, like you guys have, believe me, whatever handouts you guys have, if you have these only, and if you know how to use them, you can do a pipe stress analysis. That's how we started. I started in 1972 at Fluor. We did not have no computers. There was no explorers. It was drafting tables and manual calculations. So we had these charts here, and we did fine. There wasn't any problem. But you have to do about 30, 40 pages of calculations every day. But hey, it's been working. But now it's getting so easier and sophisticated. People don't want to understand what's behind them. You know, it takes effort to see why, what makes it go, what's the theory behind it, how we calculate. But these charts here will help you guys. If you guys ever got excited, hey, I want to check out what the loads are. You know, so sometimes curiosity brings quite a bit in you, you know. So on this one here, John, going back there. Now this page 8 is we're going to talk about here. I'll go over this one, and then probably 5:45 or so, if you guys want, or 6, whenever you guys, let me know when you guys want to go for a break. But this is the page, if you guys look at it, it's a quick check on piping flexibility. Okay. What that means here is now we are thinking about doing stress work. What are we trying to achieve? We had all the tools. We have piping components. We have all the tools available to the stress guy. We had all the pipe sports and everything there. Now, what is the stress engineer trying to achieve? This is the top thing, is trying to achieve. If you guys look at the very first line, you won't be able to read this one, but you all have the handout. The very first, the one major requirement in piping design is to provide adequate flexibility for absorbing the thermal expansion of the pipe. So what that means, the piping system should be relaxed. Does not matter which direction it's designed, which direction it's going. It should be in a relaxed position, so that means it's not putting stress in the system, or it's not creating forces. And here's the definition of piping flexibility. If we now go to the second paragraph, you say, as the pipe temperature changes from the installation condition. Now that's the base, installation condition. In the lower 48 states, we always assume the installation temperature, when they're going to install the piping, when they're going to operate the systems, before they operate the system, the temperature will be 70 degrees Fahrenheit. So that is your base. At 70 degrees, there is no thermal growth. If it's a 70 degree, you could have 200 feet of pipe. It ain't growing. It ain't moving. It's just sitting there. There's no movement, no thermal growth. So this is what we see here. The pipe temperature changes from the installation condition to the operating condition. It expands or contracts. If the temperatures are in the positive above 70, pipes start growing. If we go below 70, like some process lines, the temperature could be minus 50, minus 20, so pipe contracts. So either way, in the general term, both expansions and contractions are called thermal expansion. So when somebody talks about the thermal expansion, that means they're talking about the growth or the contraction of the pipe due to the temperature. When a pipe expands, it has the potential of generating enormous force and stress in the system. Definitely. When it's trying to expand and it's held on the ends, it's going to happen. The same way if somebody holds your arm trying to twist it, you're going to have stresses in there, and you're going to have quite a, that person has to twist with the force. The more you want to twist, the more force he has to apply. Same way as the pipes, the more it's trying to grow, the more forces and stresses going to be in the system. If the piping is flexible enough, the expansion can be absorbed without creating undue forces or stresses, which is what we're talking about, is that the piping is relaxed, there's enough flexibility in the system, we are okay. That the piping can survive, the equipment can survive. Now the problem with this, the piping is used to convey a certain amount of fluid from one point to another. We know that pipe, that's why the pipes are there. We're trying to transport liquids or gases from one place to another. Looking from the project point of view, looking from the client point of view, you want it as cheap as you can get. You want to, if you're going from this point to that point there, or 10 feet distance, you want to go straight into it, man, I'm going to buy only 10 feet of pipe. Which is good. And for the process group, it's best thing happens because they don't lose any pressure drop. Anytime you put a bend or you put extra pipe, what happens? You lose pressure in the system. Plus, if you're going further out, you're buying more pipe, you're buying the fitting, so it's getting expensive. So management, client, everybody wants to short, but it does not work for the pipe stress engineers. And they can't design nothing these days till it's proved by the pipe stress engineers. Guess what the stress engineer is going to do? Hey, yeah, this is 10 feet here, but it ain't going to work. If I have this nozzle equipment here, this is the second piece of equipment. If I'm going to start, I'm going to have 10,000 pound force. Can you take it? No, the equipment can't take it. So what we got to do, go this way, 10 feet, then we come another 8 feet that way. Now it became 18 feet. So this is expensive, plus you got some pressure drop in the system, but that's the way it's going to work. So that's what we had to do, is add flexibility to the pipe and support it. You know, this way about 10 feet going parade to there, you may not need a pipe support. But now you're going out this way, turn to 18 feet, you may have to add a pipe support. So this is what we're talking about here, the flexibility, the definition of flexibility, the application of flexibility, and the requirement of flexibility. So that's why it's very important. If you guys look the second page way on the top, see that 3 little diagrams up there? If you look the middle one, it shows the delta. The delta is the growth. When pipe got heated, it grew that far if that end is free. You know, one on the left side, the pipe is, let's see on a piece of equipment, it's a fixed nozzle. And the other side is free pipe sitting there doing nothing, which usually don't happen. This is just to illustrate the, expansion, that if it's getting temperature from the vessel, it's going to move that far out. But here's at the third, the top, they're showing other piece of equipment to the right side. Now what does that do? The third diagram shows F force. That's what's going to creating that force there. Now it's trying to resist the growth of the pipe, and it's calculated, stress is calculated here as shown on the 4th or 5th line on the left side at the bottom. F is equal to AS, because stress is directly proportional to your force divided by the area, cross-sectional area of the pipe. Or any steel, as a matter of fact, any member structure you have, whatever your force is, you divide by the cross-section there, and you got the stress in the system. So this is how that works. Now, they are recommending. Now, we know that flexibility is a must in the system, and how to achieve it. And they're shown 2 examples. We'll get to them a little later, but right now we can look at the page number 9 at the bottom. If you guys look at the upper picture, figure number 2, they're talking about the expansion loop. What that means is if the pipe is going straight so long, you got the whole pipe going to grow 6 inches, 12 inches. What are you going to do? You can't have the pipe moving 6 inches to 10 inches across the pipe racks like we saw those long lines. So what we do is we create a loop in the middle, and it absorbs like a shock. We put an anchor here, and then the pipe goes inward, and the loop inside, it gives in and out. It becomes like a shock absorber. Same with you'll have flexibility in the system. So that's what they're talking about. The best way to take care of this growth by for flexibility is have the expansion loop, or figure 3 is what we call them expansion joints. So we will talk about those different kinds too in a few minutes. So those are the best way to get rid of thermal growth if you got a lot of deflections. But for small deflections, we will go on a different page a little later. So remember that the flexibility is very important from pipe stress. Any system got to have enough flexibility, and for a high amount of expansion or contraction, you need expansion loop or expansion joint. Okay? So is that cool? You guys want to take a few minutes break, or we continue? Let's take a few minutes break.